Assalamualaikum and hello everyone. Welcome to my presentation. My name is Nukman Fatullah bin Amran. My metric ID is MA24001. Today, I am proud to present a comprehensive breakdown of the Six Sigma DMAIC methodology. This presentation was developed under the guidance of my lecturer, Professor Madya TS Dr. Haji Muhammad Haji Matno. Whether you are a student, an engineer or a business professional, understanding DMAIC is crucial for driving data-driven results. So, let's dive into how this powerful framework functions and why it remains the gold standard for continuous improvement. What exactly is Six Sigma? It serves multiple roles. First, as a statistical measure, a process sigma level indicates its overall quality. Achieving a true Six Sigma level means operating at a staggering 99.99966% defect-free rate. Second, it is a proven business strategy, originally introduced by Motorola in 1986. It was later popularized on a global scale by GE's Jack Welch during the 1990s. Third, it drives continuous improvement. It moves away from gut feelings, utilizing the data and statistical tools to eliminate defects and systematically reduce process variation. Finally, it keeps a strict customer focus. Quality is not defined by what the engineers think is good. It is defined entirely through the lens of the customer, often referred as the voice of a customer, the VOC. So now, let's look at the standard normal distribution curve. In a standard system, a baseline target might require 99.73% of the data points to fall within plus or minus 3 standard deviation or 3 sigma of the mean. However, Six Sigma pushes the boundaries of precision much further. It demands that the process boundaries expand so wide that even with a standard process shift, you experience no more than 3.4 defects per million opportunities, DPMO. This focus on process capability ensures that variation beyond these microscopic margins is caught, analyzed, and deemed completely unacceptable. In modern industrial applications, you will frequently hear the term Lean Six Sigma. It is important to understand how these two methodologies harmonize. On the left gear, we have Lean Management, which focus on improving flow, accelerating speed, and aggressively eliminating waste. On the right gear, we have Six Sigma, which focus on improving quality, eliminating variation, and eradicating defects. When you bring these two together, you will get a balanced, incredibly powerful approach to problem solving. The DMAIC serves as the central execution model for this project, giving improvement teams a complete, integrated toolkit to wipe out both inefficiency and process variation simultaneously. So now we go to DMAIC framework. DMAIC is an acronym that stands for 5 phases, which are define, measure, analyze, improve, and control. DMAIC relies entirely on evidence-based decision making. Each stage acts as a gateway. A project team must meet strict gate criteria and prove their findings with data before they are permitted to move from one operational phase to the next phase. We begin with phase 1, define. This phase is all about setting the stage. Before you try to fix anything, you have to clearly identify what you are looking at, what the boundaries are, and ensure everyone involved is on the exact same page. The core objective of the define phase is to lay a rock-solid foundation. We must define the specific problem and align stakeholder expectation. Key activities here include developing a precise problem statement, outlining clear project boundaries, identifying resource requirements, and securing project champions. To do this, we rely on a few core tools: the project charter, which defines the business case, CPOC map, to map out supplier inputs, processes, outputs, and customers at high level, and CTQs, which map out internal and external critical to quality requirements. So here, there are 3 defined tools, which is project charter, VOC, and CPOC mapping. Project charter is a vital corporate document to define the business case and precise scope boundaries. After that, VOC is active collection of customer reviews and also a feedbacks that will be translated into important metrics. After that, support mapping is a high-level diagram to show the visibility of supplier, input, process, output and customer dependencies. Now, we look at the project charter. A successful charter must clearly break down 6 core elements. 1. The problem statement. This states exactly what is wrong and how it is measured, purposely avoiding any assumed causes. Second one, the business case. This link the issue directly to financial value or customer impact. Third one, the goal statement. This must be a SMART, specific, measurable, achievable, relevant and time-bound. And then project scope. This explicitly details what is in scope and out of scope. And then 5, team roles, identifying your champion, your black or green belts, the process owner and the team members. And lastly, timeline and milestones. Setting key target dates for each phase. A standard project typically spans 3 to 6 months. Once the project is defined, we move to phase 2 measure. Now we know that the problem is we need to gather our tools, head out to the process floor and accurately quantify exactly how the process is currently performing. In the measure phase, our guiding question is, how is the process currently performing and how do we reliably measure it? We achieve this through 4 systematic steps. For the first step, process mapping, creating detailed flowcharts, value stream maps or swim lane diagrams to document every single step of the current process. Second one, data collection plan. Specifying exactly what data to collect, how to collect it, our sample size and the frequency of measurement. Third one, measurement system analysis, MSA. We run gauge R&R studies to prove our measurement gauges and tools are reliable and accurate. If your measurement system is flawed, your data will be useless. So lastly, baseline sigma calculation. This is where we calculate our starting sigma level using the recorded defects, units and opportunities via the standard DPMO formula. To understand those baseline calculations, look at the standard sigma level conversion table. The formula calculates DPMO by taking the number of defects, dividing it by units multiplied by opportunities per unit and multiplying the result by 1 million. As you can see, 1 sigma yields a dismal 30.9% efficiency, which is completely non-viable commercially. 3 sigma is an average industry standard with a 93.3% yield. But when you climb up to 6 sigma, your defect rate plummets to just 0.00034%, giving you a 99.99966% yield. This is world-class quality required in life-critical industries like commercial aviation. Next, with a verified baseline measurement in hand, we advance to phase 3, analyze. This is where the detective work begins. We have the data showing that a problem exists. Now, we must search down exactly why is it happening. Next, the primary function of the analyze phase is to isolate the true root causes of our problem. First, we must intentionally move past superficial symptoms and qualitative assumptions. It's easy for operators or managers to guess what's wrong based on experience, but Six Sigma demands validations. We formulate hypotheses and test them using strict statistical variance and correlating testing. The ultimate goal is to isolate the critical few variables that are directly driving performance failure. To do this effectively, the framework splits into qualitative and quantitative streams. Qualitative analysis focus on understanding physical process workflows and human insight. We use Ishikawa fishbone diagrams to map potential causes across the 6M: man, machine, method, material, measurement, and mother nature. We also use the 5 whys method to drill deep into operational logic origins of a failure. Next, quantitative data verification. Quantitative data mathematically prove our theory using empirical sampling before any capital is spent. We use Pareto charts to confirm the 80-20 rule, proving that roughly 80% of our defects stem from just 20% of the causes. Then, we will use hypothesis testing like ANOVA or t-test to validate significance. Let's take a quick look at the core tools we use in the analyze phase. First one is fishbone diagram. This helps us categorize potential root causes using the standard 6M framework. Next, 5 whys analysis. A simple but effective way to drill down from a surface level symptom directly to the operational root cause. Third one, Pareto chart. This visualizes the 80-20 rule, helping the team focus its energy on the vital few causes driving most of the problems. Last one, regression and hypothesis testing. This is where we bring in mathematical models like t-test or ANOVA to statistically validate which factors genuinely impact our output variables. Once the root cause is mathematically proven, we enter phase 4, improve. We know the root cause, so now it's time to design, test, and deploy targeted solutions to permanently eliminate the issue. The main objective of improve phase is to develop, test, and implement validated countermeasures. During this stage, teams conduct brainstorming sessions, run control pilot builds, and carry out Gemba walks to observe solution in real time. When picking solutions, we aim for the sweet spot on our risk impact matrix, high impact, low risk. The example of improve phase tools such as FMEA, design of experiment DOE, and 5 how. To optimize execution, we utilize Kaizen events. Kaizen events is cross-functional workshops to quickly deploy simple process changes and remove physical waste. Next, process DOE. Process DOE is systematically adjusting inputs to find the perfect configuration that minimizes system variation. Lastly, pilot proofing. It is deploying the solution on a highly restricted scale to validate outcomes and gather feedback before rolling out across the entire company. A tool used during the improve phase is FMEA, Failure Modes and Effect Analysis. It calculates a risk priority number RPN by multiplying 3 distinct factors on a scale 1 to 10. The equation is RPN equal to severity times occurrence times detection. Severity is how serious is the impact if the failure happens. Occurrence is how frequently is the failure likely to occur. And detection, how likely we to catch the failure before it reach the customer. RPN score of 100 or higher or any individual factor hitting an 8 or above act as immediate action trigger. This ensures that engineering resources are allocated to the highest risk areas first. This brings us to our final and arguably most critical phase, which is phase 5, control. Many improvement projects fail over time because teams walk away and the process slowly slips back into old inefficient habits. The control phase is designed to prevent that regression. The objective of the control phase is to sustain our optimized state and successfully hand ownership of the process back to the primary process owner. Key activities include updating all official process documentation, training field associates on the new steps, establishing continuous monitoring metrics, and formally closing out the project. Our primary tools here include SPC charts, newly mint standard operating procedures SOPs, and long-term process monitoring plans. This to ensure the gains we fought hard to achieve are locked in permanently. To guarantee the improvement we make actually stick, we deploy 4 fundamental pillars in the control phase. First one is control charts. This gives us continuous real-time monitoring over the process, immediately flagging any special cost variation. Next, control plan, a vital document detailing what to measure, how often to check it, who holds the responsibility, and the exact reaction plan if things go off track. Third one, standard operating procedures SOPs. We update or create fresh SOP to capture the newly improved process steps, completely preventing the team from reverting the old habits. And lastly, training and handover. This ensures the long-term process owners are fully capable, trained, and taking absolute accountability for ongoing performance monitoring. Let's look at the example of a control chart in action. This chart tracks our process performance across 12 weeks. The green line represents our process mean, while the red lines represent our statistically calculated upper and lower control limits. Notice what happened at week 8. The value spiked to 113, completely breaching the upper control limit. This is clear mathematical out of control signal. It alerts the process owner that a special cost variation has occurred. Instead, waiting for a month of bad product to accumulate, the team can investigate immediately, identify the root cause, and apply correction before a massive batch of defect is produced. To conclude, the greatest return of DMAIC project is not just the elimination of a single defect or saving specific sum of money. It is the cultural transformation. By forcing cross-functional teams to replace personal assumptions and corporate hierarchy with unassailable statistical evidence, the entire organization shifts. It transitions from reactive state of guesswork into proactive, highly resilient culture secured completely in objective data. It truly moved the organization from perception to precision. Before I finish, let's recap our key takeaways. First, the MAIC is a structured cycle. It is a proven methodical roadmap, not a shortcut. Second one, every phase gates the next. A weak-defined phase will lead to a faulty major phase and then will result in a wrong analysis. Third, root causes must be validated. Never guess, prove your theories with real data. The fourth one, the control phase is paramount. It is the only thing that separates a lasting process improvement from a temporary quick fix. Last one, Six Sigma is a culture. At the end of the day, it is a mindset of continuous improvement, not just a set of tools. Thank you so much for your time and attention today. If you enjoyed this deep dive into Six Sigma DMAIC, please don't forget to like this video and leave a comment. That's all. Thank you again.